Hi, my name is Michael Mustard, and today I'd like to talk to you about using concepts, not equations, for solving problems in physics. Very often when I'm working with students, I find that in physics especially, they spend a lot of time trying to think up what equation is needed to solve a particular problem. And that's really not the best way to handle problems in physics, because the truth is, there's many different situations that can arise. And if you're trying to match up some equation you've memorized with a particular situation, well, eventually you get so many different situations, it becomes a weird mixture of all sorts of things floating around in your brain. I don't know about you, but I find that really hard to do. And the shame is that physics becomes far easier when instead of trying to remember 150 different equations, you just remember a few simple concepts, and those concepts will generate those equations for you very easily. If you're new to the channel, I answer questions on math and science. If you have questions that you'd like me to answer, please put them in the comments below. And please check out the other videos on this channel. In order to illustrate this, I'm going to use an example of a fairly straightforward grade 11-ish physics problem. The setup is pretty simple. We have a skier at the top of a hill that's 50 meters high. They're not moving. Their mass is 60 kilograms. And in the illustration here, in position A, they're about to start skiing downward. Now, assuming this hill is completely frictionless and ignoring the effects of drag and so on and so forth, what we want to find out is how fast they'll be traveling when they reach the bottom of the hill. Now, a lot of time, students at this point will whip out a formula. They'll say, oh, this is great. We can solve this by saying 1/2 mv squared equals mgh. Or they'll even say, here, maybe I can use this v equals root 2gh. Now, they're correct in both cases. But whenever they do this, I ask them, where are you getting that equation from? Because in many cases, they've just memorized that this happens to be the equation that you use in this situation. That's great and all, and yeah, you'll get marks on a test. But there's things I can do to this problem to make it so that this equation doesn't work. For example, I could have said, well, instead of starting at rest, this guy's starting already moving at 2 meters per second. Your equation's not going to work. Or I could say, well, there is some friction along the surface. This skier is going to lose 500 joules of energy because of friction or drag or whatever. Well, now your equation's not going to work. So you've got this problem that you have an equation, but since you don't know where it came from, how do you know it's the right equation for this situation? And how do you know when the conditions have changed enough that this equation no longer works? And if that happens, how do you then know what the right equation to use is? You can avoid all of these problems if, instead of starting this problem with the question, what equation am I supposed to use? Instead, ask the question, what concept applies to this situation? So I'm going to solve this problem. I'm going to come up with the same answer, but I'm going to do it without having to start remembering a particular equation. What I'm going to do is I'm going to say, what concept applies in this situation? Now, for grade 11 physics questions, there's really 3 main concepts you're using in most cases. Either you're using Newton's laws and forces, and the idea that if you add up all the forces in a particular direction, that's equal to the net force in that direction, or the law of conservation of momentum, if you have a collision, or what we're going to use in this case, the law of conservation of energy. We know that in any given situation in a closed system, energy is conserved, and we're going to make the assumption that this is a closed system. If that is the case, then all I need to do is figure out what is the total energy at position A. Then I figure out what is the total energy at position B, and because energy is conserved, I know that those two energies have to be equal. So there's my concept. The concept is that the energy in the initial position is equal to the energy in the final position. Now, in this particular case, I know that this person is starting from rest, so their kinetic energy is 0, but they're starting at a height of 50 meters, and that means that they do have some gravitational potential energy. Okay? And the formula for that is m times g times h. M being the mass, g the gravitational field strength, and h the height of the hill. In the final position, I know that the skier is at the bottom of the hill, and I've arbitrarily determined that that is where we're setting our height of 0. Well, if the height is 0, then at that point, Their gravitational energy will be 0 because h is 0, but they'll have some kinetic energy, and kinetic energy is 1/2 mass times velocity squared. And now, by using the law of conservation of energy, I can say, well, the total energy in position A must equal the total energy in position B. And so mgh, the total energy at position A, is equal to 1/2 mv squared, the energy in position B. I can cancel out the m in common, move the 2 over, and have 2gh equals v squared, or v equals root 2gh, and then I can plug in the numbers for g and h to solve the problem. Now, what's great about this system is if I change the conditions subtly, because we've started with principles, we can modify the equation we have according to our principles. For example, let's say I tell you that there is some friction as they go down the hill, and that an amount of heat equal to 500 joules is generated. Well, I understand from the law of conservation of energy that that 500 joules has to come from the energy that the skier initially possessed. So all I need to do is just add 500 on the side of position B, because some of the energy went into the heat, into the 500, and the remaining will be what the skier still possesses at the bottom of the hill. And then I can solve the problem with that 500 in it all the way along. And so it's because I understand the concepts, it's easy for me to adjust the equations as needed given the situation of the problem. So I want to leave you with a couple of takeaways. First, when you're doing physics problems, don't start with an equation. Start with a concept. Start with something that is universally true, like the law of conservation of energy, not something that may be true in this particular circumstance, like some equation. The second recommendation I'm going to give you is, if you know that you're supposed to use a particular equation in a given situation, but you don't know why, try and identify what concept generated that equation and how to get that equation out of that concept. The third thing I want you to take away is this. Very often when solving a physics problem, when a student gets stuck, the first thought they have is either, what's the way I'm supposed to solve this problem? Or, how have I solved a similar problem in the past? And they try and think about other problems that they've solved. The problem with that is they don't often know whether or not the problem they're thinking of relates directly to the situation they're in right now. When you're solving a physics problem, the most important thing is to state truth. In fact, when solving any problem, stating truth is the most important starting point. If you use concepts to describe the situation you have, those will provide you with the equation you need to solve the problem. So that's how you solve problems in physics, using concepts rather than equations. If you have any thoughts or questions, please leave them in the comments below, and please check out my other videos on this channel.